This is week 8 of Applied Thermodynamics course problem solving session. So previous week we saw about internal combustion engines and so on, and how it works, and we saw heat transfer in the internal combustion engine exergy analysis. So in this week we'll see about Brayton cycle. We'll see some numericals on those, and to start with, we'll see what are the processes involved in a Brayton cycle. So I've shown two diagrams here, so two cycles in a single diagram. So okay, we have two cycles plotted in a single TS diagram. So if you see, there are two constant pressure lines, P1 and P2, which is going inside the phase boundary into subcool region and the superheated region, and there are four vertical lines. So if you see, all our vertical lines denote the constant entropy lines, or a reversible adiabatic process or isentropic process. And so there's a four processes which are reversible adiabatic compression, reversible constant pressure heat addition, reversible adiabatic expansion, and reversible constant pressure heat rejection. So these are the four processes. If you see, these are the process for Brayton cycle, and it's similar to the process in Rankine cycle as well. So the process in Brayton cycle and Rankine cycle are same. So the only difference between the both are the Rankine cycle happens inside the two-phase region, and there is a phase change happening. But in a Brayton cycle, it's a gas power cycle. So the phases involved is only a single phase of it's a gas phase operating. So it will be in the superheated region, if you see. And here in Brayton cycle, we are using air as the working fluid. So the major difference is the process. All four processes remain same, but the major difference is Rankine cycle. There is a phase change occurring during heat addition and heat rejection, and while the working fluid is still in gaseous phase in a Brayton cycle. So we'll see the components, and in general, first the Brayton cycle. So we have four processes: 1, 2, 2, 3, and 3, 4, and 4, 1. So 1, 2 is initially we take some air, we compress it, and then if you expand it again, ideally you should not get any work out, because you put in some work for compression, you get same amount of work in expansion. So to generate, you have to do a heat addition. So you do a 2 to 3, there is a heat addition. You do it at constant pressure in this case. So 1 to 2, you reversibly compress the air, and then 2 to 3, you add heat. So in this case, it could be adding fuel and combusting it, just in the case of an internal combustion engine, or you can provide heat in some other means by putting heat exchanger and heating the working fluid. So that is another mean. Or you can use just like in aircraft engines, you can put up fuel and you can combust, and you can increase the exergy or energy of the fluid. So from 2 to 3, there will be heat addition. Then 3 to 4 is your expansion. So 3 to 4, there will be expansion, and it will produce work. So out of it, some amount of fraction of the work will be used to compress the air. So the turbine drives the compressor. So apart from that, you will have some work which will be used to generate electricity, or be used for in case of aircraft engines as a thrust to move the carrier. And 4 to 1 is your heat rejection, and here we assume that this is a closed cycle. So after expansion, you are rejecting heat and you going back in the cycle. So this is an assumption which make, but in actual case, there are open cycles where after expansion you leave the gas out. So it's an exhaust which is happening in an internal combustion engine. So as the exhaust will be at higher temperature, and it will have some energy, so dumping that out is equivalent to doing a heat rejection. So same process is shown in a PV diagram and a TS diagram. In the 4% reversible adiabatic compression, reversible constant pressure heat addition, then a reversible adiabatic expansion, and then reversible pressure constant pressure heat rejection. So those are shown in a PS and a TS diagram, and this is a single stage cycle. So that's what is shown, and the efficiency of the cycle is 1 minus 1 by Rp is the pressure ratios raised to power gamma minus 1 by gamma. And here if you see if you now to increase the work output or to reduce the compressor work, what you can do is you can adopt an intercooling and reheating of an in expansion stage. So you have to go from a single stage to a multiple stage. So if you're going from one single stage to two stage, in case you have two compressors and two evaporators, so your pressure stages are different. So now the maximum compression ratio will not be P4 by P3, but you will have an intermediate pressure. So you will compress it to that and then again compress it back. You will reject some heat and you will again compress it. So in that case you will have an optimum compression pressure ratio. Also here in a Brayton cycle, your pressure when you are increasing the pressure ratio, your pressure ratio will have an optimum, because P3 to P4, if you keep on compressing, your temperature at point for the after compression could be equal to will be a very less compared to or very close to the after heat addition. So that temperature will be close. So there is effectively no heat being provided for constant pressure addition. So eventually you will not generate much work. So there will be if you go for higher pressure ratios, then your work output will be dropped to zero. And at lower compressor ratio, your pressures are very close. So eventually you are not compressing anything. So it will be very close and you are not generating eventually any work. So your work output will go through a inverted curve or a concave curve, and we will have a maximum. And maximum occurs at some pressure ratio, and that pressure ratio is given by T max by T min raised to power gamma by gamma minus 1. So sorry, gamma by 2 gamma minus 1. So that is your maximum or optimum pressure ratio for which you will get maximum work. Moving on, as I told previously, to reduce compressor work, you will adopt an intercooler, and to increase the turbine work output, you will use an reheater to eventually increase the energy of the fuel. So you are separating the compressor into two stages and putting an intercooler to bring the temperature down from T3 to ideally to T3 and T1 should be equal, and similar for and reheater, your 8 will be equal to 6. And here there is also a regenerator which is used where the exhaust temperature is used to heat the fuel going in the combustion chamber to eventually increase your utilizing heat. So that is used using an inner regenerator. So now we'll see some numericals and MCQs on Brayton cycle. Starting with, we'll see what is a major application of gas turbine is recognized for gas engines. So which type of engine prefers gas turbine cycle? So it is been asked: A, aircraft; B, locomotive; C, automotive; D, all of the above. So we know automotive uses an internal combustion engine, And locomotive is usually which run by electric or a diesel engine. Previously steam engines, now it's all diesel and electric. So and A is aircraft. So aircraft uses a Brayton cycle. So gas turbines are major applications for aircraft engines. So answer is option A. And next is reheating in a gas turbine cycle is employed to dash. A. Increase the compressor work. B. Decrease the compressor work. C. Increase the turbine work. And D. Decrease the turbine work. So we know it is to increase the turbine work. I'll go back to the circuit. See, there are two turbines, T1 and T2. So after compression, you are raising the temperature in the regenerator using the exhaust, and then you are providing heat input. So temperature will rise. So eventually the energy also rises. So the fluid, and then you are running through a turbine 1 to state T7. Then you reheat ideally to state temperature T6. So you are again raising the energy of the fluid. So now again when you run through a turbine, for that pressure ratio, your work output will be larger compared to what previously without reheating it would be. So if you assume that there are two turbines without reheating, so T7 your temperature your enthalpy at 7 will be H7. So that minus H9 would be your work output in the second turbine. Now here reheater, you are adding some energy to the fluid. So now from H7 the enthalpy will go to H8, which is higher than H7 because you are heating it. So your energy will increase. So enthalpy at 8 will be higher. So now your work output in turbine 2 will be H8 minus H9, which will be greater than H7 minus H9, which was there previously without reheat. So using a reheat, you are getting more work output. So now this is equivalent to what we saw in Rankine cycle, where we also used reheating, where it's eventually like increasing the average temperature of heat addition. So here we are doing similarly, we are raising the average temperature. So your net work output in this case with the reheater will increase. So reheating in a gas turbine cycle is employed to increase the turbine work. Moving on, we have for same power output, the overall efficiency of a gas turbine engine is dash as compared to internal combustion engine. For same power output, the overall efficiency of a gas turbine engine is dash. So comparing to internal engine, gas turbine engine will be A more, B less, C same as reciprocating engine, D none of the above. So the answer is less. So the overall efficiency of gas turbine engine will be less compared to an internal combustion engine. Yeah, because you can think a major part of it goes in compressing your air, and it operates at higher temperature as compared to internal combustion engine, and well, exhaust will be also be higher temperature compared to what internal. So you are losing large amount of heat there as well. So and on a comparison basis, gas turbine engine will be less efficient compared to an internal combustion engine. So the next question is, the specific work power output of a simple gas turbine cycle is a function of only pressure ratio. So the specific work power output of a simple gas turbine cycle, simple gas turbine is a Brayton cycle, is a function of only pressure ratio. So the answer is false. So it's not just a function of pressure ratio alone, but is also a function of maximum cycle temperature. So the answer is false. So moving on, the ideal location for placement of an intercooler in a two-stage gas turbine unit is dash. So ideal location for placement of an intercooler in a two-stage gas turbine unit is dash. In between low pressure turbine and high pressure turbine. B, in between high pressure compressor and high pressure turbine. C, in between low pressure compressor and high pressure compressor. D, in between low pressure compressor and low pressure turbine. So it's a simpler question. So intercooler we use to reduce the compressor work, because compressor, it's you can say it's directly proportional to the pressure ratios. So higher pressure ratio, higher temperature. If you reduce the temperature, you can reduce the work. So to reduce that, you use an intercooler. So it should be going between compressors, and the opposite is true in the case of turbine. So you put a reheater there in between turbines, and you put an intercooler in between compressors. So the answer is option C, in between low pressure compressor and high pressure compressor. And no point in putting it between compressor and turbine. If you really want to raise the energy of the fluid, and if you intercooler, you are bringing down the energy, you are removing heat. So that is not want. So answer is option C, in between low pressure compressor and high pressure compressor. So moving on, the next question is, the Brayton cycle which is employed in aircraft engine is dash. So the Brayton cycle which is employed in aircraft engine is a closed cycle. B, an open cycle. Either closed or open cycle. D, none of these. So in an aircraft engine, the Brayton cycle is an open cycle. So the answer is option B. So what happens in an engine is, you would have seen in an aeroplane or something, you have the engine placed in your wings. So initially you have a compressor which will draw in air, compress it, and you put it into the combustion chamber, where fuel is injected and combusted. So now the temperature is raised, and it will pass through the turbine, which will drive the compressor. So after that, what will happen? There will be a nozzle where the fluid, the exhaust is thrown out, which will create thrust. So now this exhaust is not going back. So this is not a closed cycle, this is an open cycle. So the answer is option B, an open cycle. So the next question is, at optimum value of pressure ratio, the specific work output is maximum. So this we have seen the curve that the work will go through a maxima, and it's kind of an inverted curve. So it will go through a maxima, and the work output is maximum at the optimum pressure ratio. So this statement is true. So next is, with addition of a heat exchanger, there is dash in specific work output in a heat exchanger cycle as compared to ideal Brayton cycle. So with the addition of heat exchanger, there is dash in specific work output. So this we'll see. So 19th, okay. See, so now consider this regenerator and without regenerator. That's the question. With considering heat exchanger and without heat exchanger. In ideal Brayton cycle, we don't have this regenerator. So we have compressor, we have a combustion chamber, and we have turbine. So your compressor will take in some amount of work, we assume WC, and turbine will produce some amount of work that we will consider as WT. So in the Q1 is the heat which is provided to the cycle. So now what you do is you put a heat exchanger to heat it using the exhaust. So after heating the exhaust, what's happening is your compressor, which is running between the same pressure ranges, and the temperature is also same. So what will happen is, your compressor work output will work input will remain same, WC, and the same will is true for a turbine. So regenerate, what you're adding some amount of heat from the exhaust, and it reduces the amount of heat you're providing in. So Q1 reduces, and so the turbine will also produce the same amount of work WT. So what will eventually happen is your efficiency is increasing because your heat input is reduced, but you will have the same amount of work which is produced in the cycle. So compressor will take in same amount of work and turbine will produce the same amount of work. So your net work output will remain same, but your heat added will reduce. So eventually your efficiency will change, but your work output will remain same. So with the addition of heat exchanger, there is no change in specific work output in a heat exchanger cycle as compared to ideal Brayton cycle. So the next question is, a gas turbine plant operating on Brayton cycle has maximum and minimum temperature as 800 degrees Celsius and 30 degrees Celsius. So your gas turbine is operating on a Brayton cycle. Your maximum and minimum temperatures are 800 degrees Celsius and 30 degrees Celsius. The cycle efficiency of the plant for maximum specific output is, so this is similar. I'll go back to the slide 3. So if you see your efficiency of cycle is 1 minus 1 by Rp raised to power gamma minus 1 by gamma. For optimum pressure ratio, the work output, the efficiency of the cycle is, so your R optimum is T max by T min raised to power gamma by 2 gamma minus 1. If you substitute this, the efficiency of cycle will become 1 minus root of T min by T max. So efficiency of cycle we know. So efficiency of Brayton cycle is 1 minus 1 by pressure ratio raised to power gamma minus 1 by gamma, and we know pressure ratio for optimum pressure ratios for maximum specific work output is T max by T min raised to power gamma by 2 root of gamma minus 1. So we have to just substitute that. So on substituting, we'll get efficiency as 1 minus root of T min by T max. So we know maximum temperature is given as 800 degrees Celsius and minimum temperature is given as 30 degrees Celsius. So we convert those to Kelvin. So 800 degrees Celsius will give me 107,073 Kelvin, and minimum temperature will be 303 Kelvin. And cycle efficiency for maximum specific output is 1 minus root of T min by T max. So it will be equal to 1 minus root of 303 by 800, which will give it will come out to be 0.47. So the gas turbine plant operating on Brayton cycle, the cycle efficiency for maximum specific output is operating at optimum pressure ratio, it will be 47%. So moving on to the next question. Multi-stage compression with intercooling and multi-stage expansion with reheating in a gas power plant is intended for improving the cycle efficiency. So the question is multi-stage compression with intercooling, okay, and multi-stage expansion with reheating. So it's what we saw previously in a gas power plant is intended for improving the cycle efficiency. So the answer is false. This may not necessarily improve the efficiency, but it can degrade the efficiency also. I'll explain how. So take into account this, we have two compressors with intercooler and turbines with reheater. So what will happen is you're compressing, you're taking in some amount of heat out, so your net compressor output is going down, and then you're giving in some heat. So Q1 is same, and then the turbine first stage you are producing some work, you're running between 6 and 7, and then you are again giving in some heat. So Q11 and Q12 is the heat provided, and then you are it goes to a second stage turbine, and then some work is produced. If the net work produced WT for the case 2, this will be greater than the turbine work in the without reheat. And the same for compressor. The net compressor work with intercooler will be less compared to without intercooler. So your net work output will go up using an intercooler and a reheater. But if you see, you are also increasing the amount of heat which you are providing. So Q11 plus Q12. Previously you provided only heat Q11. Now there is an increase in amount of heat which you are giving in. So you are now, previously it was only Q11, now it is Q11 plus Q12. So now the efficiency of the cycle is W net by heat input. So W net has also gone up because your compressor work has total net compressor work has gone down and net turbine work has gone up. So your total net work produced has gone up. So is the heat input. So the amount in which, the fraction in which the increase is obtained determines the efficiency. So this may not necessarily increase the efficiency of the overall cycle, it can also reduce. So for this the question, multi-stage compression with intercooling and multi-stage expansion with reheating in gas power plant is intended for improving the cycle efficiency is false. As I told, it may not necessarily improve, it can also degrade. So efficiency can go down and it can go up. So it's not assured that using an intercooling and reheating your efficiency of the cycle can be improved. So hence the statement is false. So moving on, we'll see some numericals on Brayton cycle. So we'll see some numericals on simple ideal Brayton cycle, and if it's not ideal, if your compressors and turbines are not ideal, and then we'll see some case of reheating and intercooling. So we'll see the first problem. So we have a gas turbine power plant operating on an ideal Brayton cycle, has a pressure ratio of 8. Okay, so the gas temperature is 300 Kelvin at the compressor inlet and 1300 Kelvin at the turbine inlet. Utilizing the air standard assumptions, determine the gas temperature at the exit of the compressor and the turbine, the back work ratio and the thermal efficiency. So we'll see how to solve this. So we know that it's an ideal Brayton cycle. So in the TS diagram I have plotted the 4 processes. 1 to 2 is the compression process, which is reversible adiabatic isentropic, so constant entropy, and then constant pressure heat addition in 2 to 3. 3 to 4 constant entropy, again isentropic process, then which is a turbine process, and 4 to 1 is heat rejection or exhaust. So they say that the pressure ratio is 8, so P2 by P1 or P3 equals P3 by P4 will be equals to 8. So that pressure ratio is known. And then the gas temperature at the inlet of compressor. So inlet of compressor is state 1, so we know temperature of state 1 is 300 and 1300 Kelvin at turbine inlet. Turbine inlet is state 3. After heat addition, state 3 is the turbine inlet, so that is 1300. So if you see, we know the maximum and minimum temperature for the cycle, and we also know the pressure ratio. Next we need to find out the gas the temperature at exit of each of or each of the points, and then back work ratio and thermal efficiency. So the first case is air temperatures and turbine exit temperature. So process 1-2, we know it's an isentropic compression process, and we know T1 is at 300 Kelvin and pressure ratio using an air standard table. Here with the enthalpy is at 300.19 kilojoule per kg, and we know the corresponding pressure ratio is 1.386. So PR2 by PR1 will be equals to P2 by P1. So this is at compressor exit. So your relative pressure ratio is 11.09. So for that corresponding pressure ratio and enthalpy, for a corresponding relative pressure ratio, you will have T2 as 540 Kelvin. So for that, the enthalpy at state 2 will be 544.35 kilojoule per kg. The other way of doing this is we can take temperatures T1 and T2 for an isentropic process. So P1 by P2 equals to T1 by T2 raised to power gamma by gamma minus 1. So we can use that. We know the pressure ratio, so we can easily find out the temperature. Similarly, we can find out for an expansion process. So T3 1300 Kelvin, for that corresponding enthalpy is 1395.97 kilojoule per kg. And similarly, we can find out the temperature at state 4, which is the turbine exit is at 770 Kelvin. So next question was we to find out back work ratio. Here also same, we can use an isentropic expansion formula. T3 by T4 equals P3 by P4 divided by raised to power gamma minus 1 by gamma to find out the temperature. Next is to find out the back work ratio. So for finding out the back work ratio, we know the compressor in. We have found out the enthalpies H2 and H1. So we can use H2 minus H1, or we can use straight away formula for adiabatic reversible adiabatic expansion. So we can use MR T2 minus T1 by gamma minus 1 to find out the work. Here we have found out enthalpy, so we are directly using enthalpy H2 minus H1. So it will be equal to 244.16 kilojoule per kg. The turbine out equals H3 minus H4, so 1395.97 minus 789.37, which will come out to be 606 kilojoule per kg. So turbine compressor in and turbine out is found out. The back work ratio is your work which is given in by work which is produced. So compressor in by work the turbine out. So it will come out to be 244.16 divided by 606. It will come out to be 0.403. So that is 40.3% of the turbine work output is used just to drive the compressor. So only 60%, approx 60% is what is the net work which is useful from the turbine. So next is to find out the thermal efficiency of the cycle. So thermal efficiency of cycle, we have to find out a heat in. So heat in is H3 minus H2. We know enthalpies, or you can straight away find out Cp T2 minus T1. So here we know enthalpy, so we can find out directly. So H3 130,395.97 minus 544.35 will give me 851.62 kilojoule per kg, and the net work output is 606.6 minus 244.16 will give me 362.4 kilojoule per kg. And then we can find out the thermal efficiency as net work output by heat added. So W net by Q in will give me 362.4 divided by 851.62, which is 42.6%. The other way of finding is you can use straight away use the 1 minus 1 by Rp raised to power gamma by gamma minus 1, or you can use 1 minus Q out by Q in. So we'll get the same values, 42.6%. So moving on, the next question is, assuming a compressor efficiency of 80% and a turbine efficiency of 85%, determine the back work ratio, the thermal efficiency, and the turbine exit temperature of the gas turbine cycle discussed in previous problem. So we previously we assumed that the compressor and evaporator are operating at ideally, so at reversible ideally. Now we have given isentropic efficiency of 80% for compressor and turbine as 85%. So it will cause it increase in your compressor work. So efficiency of compressor is your isentropic compressor work divided by actual compressor work. So your actual compressor work will from 244.16 will rise to 305.2. So actual compressor work will be isentropic compressor work divided by compressor efficiency. So now for this case, your compressor work will increase to 305.2 kilojoule per kg. Then similarly, the turbine output will reduce from isentropic turbine work output. So your actual turbine output will be isentropic turbine output into efficiency of turbine. So previously it was 606.6 into 0.85%. So it will come out to be 515.61 kilojoule per kg. So now the change in back work ratio is 305.2 divided by 515.61. So your back work ratio is 59.2%, which is pretty large. More than half of the work is taken by compressor. So previously it was just 40.3%. Now it has increased to 59.2. So this increase is because of the irreversibility occurring in compressor and turbine. So next we need to find out the temperatures. So we know can use the compressor formula, work in compressor formula to find out reversible adiabatic work to find out the temperature, or we know enthalpy, can find out the enthalpy at state 2a is the new state, actual state. So H2a minus H1 will be the compressor in work. So H2a will be 605.39. So your temperature at that corresponding enthalpy is 598 Kelvin, and Q in is H3 minus H2a. So H3 is 139.97 and H2a is 605.39. So the Q in is 790.58 kilojoule per kg. So H3 remains same as the previous one, and the net work is W out minus W in. So we know W net, W out is 305.2, sorry 515.61 minus 305.2, which will come out to be 210.41. So if you see, if thermal efficiency is W net by the heat added, W net is 210.41 kilojoule per kg. So divide by heat input which we have calculated is 790.58 kilojoule per kg. So the total thermal efficiency of the cycle is 26.6%. So we have calculated the thermal efficiency of the cycle. So next is, if you see, that is irreversibility occurring within the turbine and compressor caused the thermal efficiency. So previously the thermal efficiency was 42.6%. Now it has reduced to 26.6%. So this example shows how sensitive the performance is to the gas turbine and compressor efficiencies. So maybe if your turbine and compressor are not efficient, your there will be a huge drop in compressor your cycle efficiency. So next was to find out the turbine exit temperature. So we know the turbine output is 515.61 and your network output is H3 minus H4A. So enthalpy at state 4A is 880.36 kilojoule per kg. So your temperature corresponding to that enthalpy will come out to be 853 Kelvin. Hello. அது கீழே ஒரு 9 ஒரு நம்பர் போட்டு பாக்ஸ் இருக்குமா, அதில் வச்சுருங்களா? தேங்க்ஸ். ரெண்டு இருக்குது, அதில் வச்சுருங்க. கீழே 9 நம்பர் பாக்ஸ் போட்டு கீழே இது இருக்கும், அங்கேயே வச்சுருங்க. ஏன்னா இப்போ வெளியே இருக்கேன், ஒரு அரை மணி நேரம் ஆகும் வர்றது. ஓகே. So moving on, so we have a thermal efficiency of the gas turbine. So previous problem we saw how your turbine and compressor efficiency is affecting the thermal efficiency of the cycle. So now what we do is use a regenerator. So you are using a part of the heat. You know that exhaust is a higher temperature. So in actual cases, your exhaust will be at higher temperature. So you use that to heat to the incoming fluid to the combustion chamber. So you are reducing the part of the energy provided in the combustion chamber. So heat input is reduced. So you see, I have shown the cycle in a TS diagram on the right. So 1 to 2A is the actual process for compression. Then 2A to 5 is for the heat provided with the regeneration. Then 5 to 3 is the heat provided input. and 3 to 4a is your turbine work, then 4a to 1 is the heat rejected. So you'll see, we know here that regenerator is of effectiveness 80%, which is installed. So if the heat regenerator is of 80%, then the maximum heat which it can provide is 4a minus 2a, H4a minus 2a, and the actual which is obtained is 5 minus 2a. So the maximum is, if you see, this is being counter flow. So maximum which is obtained when 5 and 4 the fluid coming in to the regenerator from the turbine, if that is equal to the enthalpy of state 5, that means the regenerator is 100% effective. So your whatever heat fluid is coming in from the turbine and what is going out, so it will be the temperatures are same. So in this case the enthalpy is, because same fluid, your temperatures are same, or in sense the enthalpies are same. So what will happen is effectiveness will become 100%. So it will be say longer heat exchanger, there will be very small temperature gap, or there is a temperature is negligible. That's when your heat exchanger, you say it's 100%. So 5 will become 4a. So effectiveness is defined as Q by Q max, and the maximum heat which can provide is H4a minus H2a, and the heat obtained by the fluid is H5 minus H2a. And we know that effectiveness of heat exchanger is 80%, so 0.8. So now we can find out state at 0.5 H5, which will come out to be 825.37 kilojoule per kg. And we know the enthalpy at state 3 is 1395.97. So now the total heat added is 570.60. So now what happened is, so there is a saving of 220 kilojoule per kg of heat, which is previously was given, now it's avoided because of regenerator. So this addition of regenerator is not affecting any of the work output, so the work output will remain same. So previously the work output, the net work output was 210.41 kilojoule per kg, so that will remain same for this case as well, but there is a reduction in heat input, so it will be 570.60 kilojoule per kg this time. So the total net thermal efficiency is 210.41 divided by 570.6 kilojoule per kg. So now it is 36.9%. So if you see, previously without this regenerator your thermal efficiency was 26.6%, and now it has rise to 36.9 with addition of regenerator, and you're utilizing the energy which was going waste in the exhaust. Now you're utilizing that to heat the input, and which is reflecting in the thermal efficiency. So the next question is, and you have an ideal gas turbine cycle with 2 stages of compression and 2 stages of expansion, which has an overall pressure ratio of 8. So air enters each stage of the compressor at 300 Kelvin. So and the turbine at 1300 Kelvin. So determine the back work ratio and thermal efficiency of this gas turbine cycle. So if you see, the maximum and minimum temperature is same as the previous problem. So now instead of a single stage, we have converted it into a two stage. So initially at 300 Kelvin, the compressor, we have raising that, compressing it to state 2, and then we are passing it through an intercooler to bring down the temperature of the air to state 3, which is same as state 1, 300 Kelvin, and then compressing it again. So this overall pressure ratio P4 by P1 is 8, and we are doing in heat addition, and then from 6, which is at 1300 Kelvin, to the inlet to the first turbine, we are expanding it to state 7, and then reheating again to state 8, which is same as 1300 Kelvin, and then bringing it back and then expanding it again. Ideally, if you see, state 5, 7 and 9 will coincide for an ideal case, and similarly 4, 2 and 10 will remain same. So corresponding H5 will be equal to H7 will be equal to H9, and H4 will be equal to enthalpy at state 4, 2 and 10 will be same. So ideal cases, these are ideal assumption. We are doing an ideal gas turbine cycle. So now we know how the cycle operates. Now what has been asked to find out is determine the back work ratio and thermal efficiency of this gas turbine cycle, assuming no regenerators are used. So it's there is no regeneration, there is no heat addition being done from the exhaust. So that's the first case. And if ideal regenerator with 100% effectiveness, so 100% effectiveness is used, then how is the back work ratio and thermal efficiency? So for two-stage compression expansion, the work input is minimized and work output is maximized when both stages of compressor have same pressure ratio. So P2 by P1 equals P4 by P3 will be root of 8. So it will come out to be 2.83. The pressure ratio is 2.83 between two stages. So air enters each stage of the compressor at the same temperature and each stage at the same isentropic efficiency. Because in this ideal cycle, we are assuming compressors are 100% efficient and turbines also 100% efficient. At inlet, so T1 will be equal to T3, so H1 will be equal to H3, same T6 equal to T8 and H6 equal to H8, and then T5, T7, T9 and same T4 to T2, T10. So first case is assuming there is no regeneration happening. So in that case, what will happen is, for temperature T1 equal to 300 Kelvin, from air standard table, we'll get table that temperature T1 for 300 Kelvin, the corresponding enthalpy is 300.19 kilojoule per kg, for which the pressure relative pressure ratio is 1.386, and similarly we can find out for state 2, the temperature T2 will be 403.3 Kelvin, and corresponding enthalpy is 404.31 kilojoule per kg. The alternative way is, as I told previously, this is an isentropic process, so we can use P2 by P1 equals to T2 by T1 raised by gamma minus 1 by gamma to find out temperature for all the states. The similar process is adopted to find out each of the pressure and temperature. So we have found using each of the states temperature and pressure, we can find out the enthalpies. So we have found out the enthalpies as well. So now we can calculate the compressor work in each stages. So compressor work 1 will be 2 equals because it's operating between two same pressure ratios and the temperature, and so the work also will be remain same. So W compressor in will be twice the compressor in a single stage. So twice into H2 minus H1 will become 2 into 404.31 minus 300.19. So which will come out to be 208.24 kilojoule per kg. Similarly, the turbine outlet temperature is twice the work produced in a single turbine. So it will be 2 into H6 minus H7. So 2 into 1395.97 minus 105.33, which will come out to be 685.28 kilojoule per kg. So the net work is the turbine outlet minus compressor in will come out to be 477.04 kilojoule per kg. So Q in in this case previously, as I told, compressor work, you can, if you can find out enthalpy, you can directly calculate enthalpy, or the other way of doing is you can use the isentropic formula, which is gamma R T2 minus T1 by gamma minus 1. That is one way. Or you can find out using enthalpy value. So now we found out the net work output, and Q in is Q primary plus the reheat which we are given. So Q is H6 minus H4 plus H8 minus H7. So that is the net heat addition, which will come out to be 1334.30 kilojoule per kg. So thus your back work ratio is compressor in by turbine out, which will be equal to 208.24 kilojoule per kg divided by 685.28 kilojoule per kg, which will come out to be 0.304, and the thermal efficiency here is W net by your back work ratio is compressor in by turbine out. So compression in work is 208.24 kilojoule per kg, and turbine out work is 685.28 kilojoule per kg, which will come out to be 0.304 or 30.4%. So this is that 30% of the compressor work is utilized, which is generated in the turbine. And then you can find out the thermal efficiency, which is nothing but W net by Q in, equals 477.04 kilojoule per kg divided by 1334.30 kilojoule per kg, which will come out to be 35.8%. So this was assuming there is no regenerator use in this cycle. If we use a regenerator, so comparison here, what will happen is compression for the result single stage compression reveals that multi-stage we'll first compare. We saw the same problem with maximum temperature of 1300 Kelvin and 300 Kelvin. So there we saw for an ideal cycle for a single stage we got efficiency of 40.3%, and now we see that it's a drop in efficiency. So using an intercooler and reheater may, as I told previously, may not always result in an increase in efficiency. As you can see here, it has reduced from 40.3% to 30.4%. So sorry, back work ratio reduces from your thermal efficiency reduces from 42.6% to 35.8%, and back work ratio is also reduced. So if you see previously in a single stage turbine, 40% of the turbine work was utilized in compressor. Now that has reduced to 30%. So there is a saving in work which is generated, but your thermal efficiency is reduced. You are compromising in thermal efficiency, but you are producing more work. That's what is happening when you are using an intercooler and a reheater. So now adding an idle regenerator of 100% will not affect your work. So your work output, which is generated net work output, will remain same, But what will happen adding an idle regenerator, you are utilizing some amount of exhaust to heat the inlet. So now what will happen is your Q in will be H6 minus H5 and H8 minus H7. So H6 minus H5. Previously what happened is your initial heat provided to the cycle was H6 minus H4. Now what will happen is your turbine exit is at 9 and so you are using you are putting a regenerator. So this regenerator is of 100% effectiveness. So your enthalpy difference will be H9 minus H10 will be equal to H5 minus H4. So this amount of heat is provided by the regenerator. So the additional H5 minus H6 is the one which it should be provided externally. So the heat input which you are providing with an ideal regenerator is H5 minus H6 plus H7 minus H8. So substituting that, we'll get that the heat added is 685.28 kilojoule per kg. So now substituting this, efficiency will become W net by Q in will come out to be 69.6%. So if you see, this is a larger increase. If you see the previously for single stage it was 42.6%, and if you see the previous case, efficiency is close to 36%. Now it has gone up to 69.6%. So what will happen is now we consider two cycle efficiency for a two-stage compression. What happens if you keep on increasing the number of stages? So if you see now, if you keep on increasing the number of stages, it will become close to Carnot cycle, or the term is called an Ericsson cycle. So it will become close to that, and the efficiency for that will be Carnot efficiency. So maximum it will give you 76.9%. So in that case, your pressure ratios, if you cannot achieve that, because your pressure ratios in each of the cycle will be very less, because you are putting n number of or infinite number of cycles. So your pressure ratios will be very less, but you'll reach Carnot efficiency. So 76.9% is the maximum efficiency which you can achieve. So now if you see, it's very close. 69.6% is a good amount of efficiency, and you putting an infinite number of cycles, you are only going to 77%. So it's just close to 7%. So increasing the number of stages may not effectively give you rise in thermal efficiency compared to cost. So now two things comes into play. So now two things comes into play. Increasing the number of stages will cost you in terms of money in the initial capital cost, but previously first for two stage, from single stage to two stage, for an ideal cycle you are going from 42.6% to 69.6%, and again increasing in another stage you are putting in another turbine and compressor, an intercooler and reheater. This all will cost an increase in money, but you will not get that much of amount of money in terms of returns. In terms of efficiency, there will be not a bigger difference in efficiency increasing the stages from here on. So the next question is, and before going back, so here in this case I used in all the problems I used n actual air standard values, so actual values of an standard values of air. So this value will be different because this will take into account the variation in specific heat of the air, but this is not if you calculate this with respect to constant Cp value, this value may differ. There will be difference in the value of all the work output and thermal efficiency, because here the values which enthalpy values which has been taken or the actual air standard values. So if you assume that the specific heat is constant with respect to temperature, this value will be different, and your enthalpy's values will also be different, and your work output and eventually the other values will also be different. So moving on, so there are two approaches. So basically for solving any problem you have two approaches. One, you can use an actual standard values which are available. So you can search for an air standard table and you can use that values to calculate, or you can calculate using assuming an ideal case, assuming that air is an ideal gas, and you can solve using that. So while solving, I have described both the ways of solving. One is the process which is shown, and other is using the ideal gas values. For example, for finding out the compressor work, you can use the reversible adiabatic compressor work to solve it, or you can straight away find out the enthalpies as I did in the problem. So okay, so moving on, the next problem is an industrial plant is equipped with a regenerative gas turbine cycle as shown in figure. The air inlet condition at the compressor are 101.325 kilopascal and 27 degrees Celsius. The compressor pressurizes air to 10 times the inlet pressure. In addition, the maximum air temperature in the gas turbine is measured as So air inlet condition at the compressor are 101.325 and 27 degrees Celsius. The compressor pressurizes air to 10 times, so the pressure ratio is 10. So maximum air temperature in the gas turbine is 790 degrees Celsius. A temperature difference of 10 degrees Celsius is measured between the cold air stream leaving the regenerator and the hot air stream entering the regenerator. So the net mechanical power output is 106 kilowatt and heat input source temperature is 2500 Kelvin. So, and again they are given isentropic efficiencies as 87% and 85% respectively. So we have been asked to find out, determine heat rejection and addition rate for both the actual and ideal cycles, determine the entropy generation rate in combustion chamber, find the exergy destruction rate in the combustion chamber, and then determine the exergy efficiency of the cycle. So now this is the cycle which has been described in the problem. So this is just a regenerator cycle which we saw previously. So here they have given that the temperature difference is of 10 degrees Celsius between the cold air stream leaving the regenerator and the hot air stream entering the regenerator. So there is a temperature difference of 10 degrees Celsius. Between state T3 and T5. So now we will see how to solve this problem. So here again previously I showed using using the table values for air. Now I have taken a problem where I assume that the pressures are your specific heats and gases and ideal gas. So here your temperature at state 2 is equals to state T1 into pressure ratios into raised to power gamma minus 1 by gamma. So state 1 is 300 Kelvin and your pressure ratio is 10 and gamma is 1.4. So 0.4 by 1.4 will come out to be 579.2 Kelvin. So state 2 for ideal case is 579.2, but we know that the efficiency is 87%. So we can calculate the efficiency here in terms of I have written in terms of temperatures. If you see H2S minus H1 divided by H2A minus H1, is equals to the isentropic efficiency of the compressor. So Cp is same, so you can write it directly in terms of temperatures. So it will come out to be at state 2, the temperature is 620.9 Kelvin. Similarly, the isentropic temperature at state 5 can be evaluated as T5s equals T4 into 1 by compression ratio L raised to power gamma minus 1 by gamma. So T5 will be 16063 Kelvin into 1 by 10 raised to power 0.4 by 1.4. So this will come out to be 550.6 Kelvin. So next is to find out the actual cycle efficiency, because the isentropic efficiency of turbine is 85%. So we can express T5 as T4 minus efficiency of turbine into T4 minus T5s. So it's just basically actual by isentropic work. So in terms of enthalpy, you can neglect C. You can remove Cp. So you'll get efficiency in terms of temperature. So now state 5, the temperature will become 627.4 Kelvin. So then you're doing an energy balance across the regenerator. We know that m.3 minus m.3 into h3 minus h2 will be equals to m.h5 minus h6. So now taking all converting that into temperature will give me T2 minus T3 will equals to T6 minus T5. So we know that So we know that the previous problem T3 minus T5 is 10 degrees Celsius. This is given in the problem. So we substitute that. On substituting, we'll get a T3 is 617.4 Kelvin. So on substituting in the relation previously, T2 minus T3 equal to T6 minus T5, we can find out this temperature T6, which will come out to be 631 Kelvin. So the net power output is known to be from the problem as 106 kilowatt. So using this we can find out the mass flow rate. So mass flow rate is m dot a into W net by specific work output, and specific work output is your compressor work minus turbine work. So H5 minus H4 or Cp T5 minus T4 and minus Cp T2s minus T2 minus T1. So that is what is written. So substituting Cp as 1 kilojoule per kg and the temperature which we have calculated in kelvins, and W net is 106 kilowatt. So we'll come out mass flow rate is 0.9241 kilojoule per kilogram per second. So this is the actual mass flow rate. If you see, the ideal mass flow rate is W net by specific work output for an ideal case, which will come out to be 0.455 kg per second. So if you see, this is close to twice the mass flow rate for an actual case. So next is heat added. So heat input in the combustion chamber is m.4 H4 minus H3. So this will come out to be m.a Cp T4 minus T3. This will, on substituting, will give me 413.8 kilowatt. Similarly, for an ideal case, the heat input is 203.8 kilowatt. The next is was to find out the heat rejected. So Q rejected is H6 minus H1 in m.a into Cp T6 minus T1, which will come out to be 307.4 kilowatt for the actual case. If you see, consider an ideal case, it will be 149.7 kilowatt. So now we have calculated all the heat input and heat rejected. So next is to find out the entropy generated in the combustion chamber. So if you see combustion chamber, the Sgen is the entropy coming in. Okay, let's go back. So this is the combustion chamber. So you have coming in S3, you're going in S4, and heat there is added. So QC by T source, which is coming in, plus D3 S3 equals S4 plus Sgen. So that is the combustion chamber entropy balance. So you're doing an entropy balance. So Sgen is what we have to find out. So m dot 4 S4 minus m dot 3 S3 is the entropy going out minus coming in minus heat added, QC by TS. So for at state 103.25 and T4, your entropy is 6.376 kilojoule per kg, and S3 is 6.175 kilojoule per kg for pressure, corresponding pressure and temperature. So using this, substituting that value and mass value 0.9241, and we have calculated the Q value is 413.8 kilowatt, and the source temperature is given as 2500 Kelvin, which will come out to be 0.02 kilowatt per kilowatt Kelvin. So now we found out the entropy generated in combustion chamber. Next is to find out the exergy destroyed. So we'll do an exergy balance across the compressor. So m dot 3 x3 is exergy coming in, and q dot c into 1 minus t naught ts is exergy coming in through heat, and m dot 4 ex4 is exergy going out, and some exergy is destroyed. So we can find out exergy 3 and similarly exergy 4. So substituting these values in exergy balance equation will come out exergy destroyed as 238 kilowatt. So you can calculate otherwise using T naught into delta S or Sgen. T naught plus Sgen will also give me the exergy destroyed in combustion chamber. So next is to find out the thermal efficiency and exergy efficiency. So thermal efficiency is W net divided by Q added. So W net is 106 kilowatt, which is given in the question, and Q net is 413.8 kilowatt, which will come out to be 25.6%. And then the exergy efficiency is the W net divided by exergy added in combustion chamber. So 106 divided by 413.8 into 1 minus 300 by 2500, which will come out to be 29.1%. So exergy efficiency is 29.1% and your thermal efficiency is 25.6%. So that's all for today. Thank you.